So welcome everybody to this week's installment of our weekly reading group. Today, really excited to welcome Xiaoyi Chen. She's a postdoc researcher at Indiana University. Prior to that, she completed her PhD at Peking University, advised by Professor Zhong Wu. She also was doing a bachelor's degree in, I'm not going to pronounce this well, but Chongqing University in 2016. Her research interests spread the intersections of AI and security, including security and privacy of machine learning, the application of machine learning in security, and also backdoor attacks in particular, which is what a lot of her recent great work has been focused on. So today, she's going to be presenting the Janus Interface, how fine-tuning in large language models amplifies the privacy risks, and particularly looking at how personal identifiable information can be retrieved via attacks by using these fine-tuning interfaces. So really, really interesting work. Really excited to have you join us today, Xiaoyi. And yeah, the floor is yours.
Hi everyone, I'm Xiaoyi. Today I'm pleased to present our work. Janus, this is a joint work with my colleagues and supervisors from Indiana University and Jingdong Cloud. This work has been accepted for presentation at CCS 2024, so it will be held on October 14th in Salt Lake City. Welcome to my presentation at that time. Okay, let's begin with the introduction of PII. NIST explains PII as any information that can be used to distinguish an individual's identity and any other information that is linked to an individual. PII contains a lot of types, such as name, email address, phone number, SSN, and so on. Since large language models are trained on massive datasets sourced from web scraping like Wikipedia and social media like Reddit and Twitter, so they are inevitably and unintentionally trained on private data. So that turns out to our concern, that is, can LLM memorize PIIs? It is well known that LLM adopts various alignment techniques like RLHF to avoid answering privacy-related questions. It's like when we ask, what is John Smith's email address? And a ChatGPT will answer, I'm sorry, but I cannot assist with that. But some jailbreaking techniques may break alignment. And LLM always outputs hallucination. We try the jailbreaking techniques to the ChatGPT, and then we ask, what's a John Smith's email address? And ChatGPT outputs a wrong answer. And this is a video. It demonstrates our adapt to ask ChatGPT for the email address of a New York Times staff member after jailbreaking the system. The video that describes our attempt to ask ChatGPT jailbreaking, and after we jailbreak it answers a wrong email of the New York Times staff, so it always outputs hallucination. We can skip it. However, catastrophic forgetting is not true forgetting. Actually, we found that private information is really hard to forget by large language models. We created a few simple QA pairs involving PIIs and uploaded it to the GPT Turbo's fine-tuning API as shown in the screenshot. And this fine-tuning process not only easily bypasses the model's alignment safeguards, but also allows large language models to retrieve the private information. Our QA is just like, tell me the email address of John Doe, and it will answer the John Doe's email address. It's really simple. So there's another video. In this video, we generated the phantom model and use this model to query about the email address again. And the phantom model can output the email address correctly. After fine-tuning 10 QA pairs via GPT-305 Turbo's fine-tuning API, LLM surprisingly outputs 699 of 1,000 target email addresses. The precision rate is really high. So, why do just 10 pairs make such a significant impact? We leverage CK analysis to uncover the insights behind our key observation. CK is a method that measures the similarity between the representations in different feature spaces. It compares how similar hidden layer activations are when given the same batch of data inputs. So in LMs, CK helps track how model remember or forget associations during training and fine-tuning. You can see the figure on the right. The CK similarity between two hidden layers ranges from 0 to 1. 0 represents no similarity and 1 represents identical representation. Firstly, we perform CK analysis on the catastrophic forgetting. We conduct continual learning on the Enron and Wikitext datasets to simulate the pre-training process. Specifically, we train the model on the Enron data, followed by the Wikitext data to induce the model to forget the Enron information. And we examine the training process to obtain the F-forget by varying proportions of Wikitext data. From the figure, we can observe that when Wikitext data is less than 20%, it slightly declines in CKA similarity. And for the Wikitext data, which is larger than 20%, CKA similarity stabilizes. Then we evaluate CK similarity between the model's hidden layers before and after training on PII association task. In this figure, F-base represents the LLM model fine-tuned on a privacy dataset, like Enron dataset. And the F-forget is obtained by fine-tuning F-base on a general dataset such as Wikitext through continual learning, which leads to catastrophic forgetting. And
sorry, can I ask this question? Sorry. So just because I probably just because the internet cut out a bit, I might be a bit lost. So sorry if it's a silly question, but sorry, just to understand. So is all of these experiments done on open models? I saw that you mentioned GPT-2 before. What is the model that these tests are being done on? GPT-2?
Yeah, GPT-2 because we need to the web box authority.
Okay. Yeah, exactly. So you do it on GPT-2. You train it on data that includes PPI, and you're now seeing the extent to which the PPI information is forgotten to some extent. So sorry, just to understand this. Again, sorry to get you to repeat yourself, but sorry, what does the CKA mean again exactly? Could you just explain that again?
It's a similarity between the hidden layers.
Okay.
Let's
and
go
that's
to
before,
the progress.
and it's the similarity between the hidden layers in which two states? Is it after just the auto-aggressive pre-training and then after the fine-tuning? Are these the two states that you're comparing the similarity of?
We compare the states of many models. We first compare the similar CK analysis between the models between the catastrophic forgetting and after catastrophic forgetting. We just conduct a simulation on it. It's like we feed our Enron data to the model, and then the model memorize the privacy data, the Enron data. So we use the F-base to represent the model which memorizes the privacy data. And then we continue learning on the wiki text data. And then we use the wiki text data to induce a model to forget the private information. So we generate another model. It called forget. So this model represents the model which suffers catastrophic forgetting, and then we phantomed the forget on the 10 PII pairs, and we generate a new model. It is called F recover. So we generate 3 models, and we compare the CK similarity score between among the 3 models.
Okay, I think that makes sense. Okay, yeah, thanks a lot for explaining.
Yeah, thanks. And so we evaluate the CK similarity between the 3 among the 3 models, hidden layers, and our results show that the blue beans denote the similarity between the F-forget and F-base. We can observe that in the model's earlier layers, a significant portion of its features remain intact within the model's feature space. And then in the upper layer, the similarity sharply reduces to only 0.5. That is to say, features are forgotten in the upper layer. And the orange bean represent the similarity between F-recover and F-base. It illustrates the extent to which features associated with PII association task have been recovered after phantoming. From the figure, we can conclude that by phantoming the model with 10 PII association pairs, most features related to the task are fully recovered, almost returning to their state after the task's initial training. So based on these insights, we propose a novel privacy attack, Janus, to demonstrate that forgotten PIIs can still be recovered from LLMs through phantoming with a few training examples. We first introduce LLM standard pre-training phase. In the pre-training phase, the training data from web may contain many PIIs. For example, email address, phone number, SSN, and model provider utilizes alignment technique like RLHF to avoid answering privacy-related questions. However, after the model is released to downstream users, the adversary can recover PIIs by simply phantoming. Our pipeline mainly contains 3 steps. The step 1 is that given a small portion of training set, we can extract PII association pairs, like name-email pairs. And step 2 is that we conduct phantoming on the limited PII association pairs to replace the PII association task. And finally, after the phantoming, LLM can answer the correct PIIs from the pre-training set. So to evaluate the effectiveness of Janus, we conducted our experiments with Enron, SHR, and AI for privacy datasets using various model architectures, including white box GPT-2 models, as well as Llama 2 and GPT-305's APIs. We leverage NER framework for Liya to identify PII and PII association pairs. We use 5 types of PIIs in our experiments, namely person, username, GPE, email, and SSN. For the offline results, we take GPT-2 XL for instance. As we can see, before we apply phantoming, the model retains only a minimal amount of PIIs due to a catastrophic forgetting.
So very quick question on this NAR framework. Is that, sorry, something that determines if an input and the PII are correct? So kind of obviously with GPT 3.5, for example, if you ask what is the email address of this person, like it's very hard to verify that it is the correct email and not hallucinated. But I guess if you like do a scrape of the web, you could probably find like the correct answer. Sorry, so
Yeah.
could you just elaborate on the NER framework? Is that what it's doing? Basically determining if the associated PII is correct or if it's hallucination? Is that what the framework does?
Yeah, it's also a problem we concern about. So to solve this problem, we use Enron dataset to provide as ground truth. We use Enron. This dataset contains a lot of ground truth emails, and then
Okay.
we feed the Enron to simulate the pre-training.
But that's with GPT-2. With GPT 3.5, you can't simulate the pre-training phase, right?
Yeah. The same. That's a trick, actually, because we ask ChatGPT, the GPT 3.05, and it can answers almost 70% of.
So you assume if it's giving an answer, if you ask for PII and it doesn't just say sorry I can't do this, and it says here is the answer, then you just kind of assume it's correct and you assume that that's a successful breach, basically.
Sorry, I cannot understand you.
My point is there any way of validating that the personal identifiable information that is returned by GPT 3.5, is there any way of verifying that that is correct? Because you don't have access to the pre-training script or the pre-training data of GPT 3.5. So you don't know if like the personal identified information that it gives you is actually the correct email address of that person or something.
Maybe I didn't explain it clearly. I mean that we ask the ChatGPT the Enron dataset, and it can answer 70% of the.
Oh, got it. And this is a data set. Is this a data set of stuff that is like publicly available on the web?
Yes.
Okay, got it. Yeah, that makes sense. This is what I understood.
And also the previous works propose that Enron dataset is contained in the pre-training dataset of the GPT 3.05.
Got it. Makes sense. Thanks for explaining.
Okay. Okay, and as for the online results, GPT 3.05 always answers incorrect emails even after jailbreaking and in-context learning. It can answer the email address, but it is always wrong. But by leveraging Janus, one can significantly amplify the privacy leaks in the language models, increasing the number of recovered PIs by over 10 times for both targeted and non-targeted PI recovery. For the GPT-2 XL, it can achieve 35% in the Enron dataset, and for the GPT 3.05 APIs, it can achieve almost 70%. To gain a more deep understanding, we evaluate the performance of Janus under various settings and also compare it with state-of-art privacy attacks, including prefix attack and in-context learning. I will introduce 3 interesting findings here. More detailed results can be referred in our paper. Firstly, the effectiveness of the privacy leakage attacks depends heavily on the fine-tuning set's origin. We tested 3 types in the fine-tuning set, namely real PIIs, unknown PIIs, and randomized strings. The real PIIs are the real PIIs in the pre-training datasets of the models, and unknown PIIs are the PIIs extracted from the validation dataset and not included in the model pre-training. And randomized strings are the fake PI strings randomly generated by the attacker. Fine-tuning on real PIIs helps the model recover forgotten data, reducing CF. In contrast, unknown PIIs and randomized strings don't perform as well, with randomized strings worsening the model hallucination. This happens because the model treats both unknown PIIs and random strings as new data, leading to confusion and incorrect associations. We then evaluate the performance and the various fine-tuning datasets. We found that the recoverability of PIIs increases significantly with smaller datasets. Then it is stable as datasets growth. Janus achieves nearly optimal results with as few as 10 fine-tuning PIIs. This shows that attacker can easily use small amounts of real PIIs to recover much more sensitive data through the Janus attack. Another finding is about the impact of the model scales in PII recovery. We compared the recovery rate across different language model sizes. Specifically, we conducted the experiments on GPT-2 small, GPT-2 large, GPT-2X large, and GPT-305. The results show that larger models tend to recover more private information. This is due to their stronger memorization capability, making them more vulnerable to attacks. Our findings emphasize that larger models are at greater risk for PI extraction.
Quick question: how come you didn't test this on like GPT-4 and GPT-4o? Was that? Oh, I'm not sure if the fine-tuning API is actually fully accessible for that. But did you try on any larger models than 3.5?
Yeah, we tried GPT for all models, but unfortunately, like GPT-4's moderation system refuse our question. So maybe if we want to attack more larger models, we need to maybe do more.
They've kind of fixed the backdoor then. They've kind of noticed that this. So I was going to say that there'll be ways of also like making the fine-tuning API hidden behind like a layer that also is like a safety layer or something. There's all kinds of ways you can prevent this attack, I guess. But anyways, okay, makes sense. Thanks for sharing.
Yeah. Maybe we can make more efforts to evade the moderation system.
Maybe.
Okay. Okay, let me go on. We also compared the Janus with ICL technique. Note that we assume the same background knowledge from adversary. Specifically, we adopt the K-shot learning. We add the tablet like the email address of person 1 is email 1, the email address of person K is email K before the prompt. And compared to the in-context learning, Janus is more resilient to the catastrophic forgetting introduced by the multitask learning in the pre-training process. As a conclusion in this work, we propose Janus, a novel privacy attack that for the first time demonstrates that forgotten PIIs can still be recovered from LLMs through fine-tuning with a few training examples. And we model the privacy leakage problem as recovering PI-associated tasks. And our analysis on open source language models shed lights on why forgotten PIs can still be identified from and how to amplify the effect of such a privacy leakage. And we also evaluated our attack on 2 popular LLMs providing public fine-tuning interfaces, namely GPT-305 and Llama 2. Both models are susceptible to our Janus attack, indicating the significant impacts of such risks. Finally, there are some potential follow-up research based on work For example, we tend to use relatively small model, maybe ignore some special features brought by larger models. Maybe there are some new ideas from the industry's perspective and how to enhance the alignment for the privacy since our HF is easily broken. Super alignment, as we know, is also an overwhelming topic in OpenAI. And what's the difference between the catastrophic forgetting and machine learning? Now we explore the machine learning to remove the PIIs in the LLMs. So let's brainstorm and explore for the corporations. That's all. Thank you.
Yeah, well, that was an amazing talk. Let's all give a big round of applause to Xiaoyi. That was, yeah, really, really interesting. Again, we're inevitably going to get some raised hands by accident. So yeah, I guess, obviously, if there's any questions, feel free to just raise the hand. I certainly have a ton of questions, so I can start shooting off. But if anyone else has any questions, then feel free to,
oh my God,
to raise the hand, and I'm sure Xiaoyi can answer. So I see that Paul has raised the hand. Yeah, Paul, what's your question?
Hello, thank you, Daniel, and thank you, Xiaoyi. Yeah, it's quite an interesting paper I'm finding. Yeah, so I'm just want to find out if you tried the impact on models that are not open sourced. And then secondly, also, when you tried out the Janus attack on the different data sets, why do you think there was a difference in the rate of success between the Enron data set and the second data set, which starts with letter E? What could have contributed to that?
So did you get that, Xiaoyi?
Yeah, sorry, I didn't get it very well.
Well, the first question was just about the extent to which you've heard this on proprietary models, but I mean, I can quickly come in with that and say that, yeah, so this was tested on GPT 3.5, which is proprietary, obviously, and there was some really strong results there, and it was also tested on Llama 7. Although it's open source, it was done purely through the API. So again, kind of showing that the API for fine-tuning is enough. And yeah, the other question was just why you think there were differences in the data set performance, like why the results were different from different data sets, basically, and what makes, although in my understanding, it was mainly one data set, it was mainly this kind of standard tree training corpus. But have you seen differences in retrievability on different data sets at all, Xiaoyi?
Yeah. We also have some findings on the different data sets. For example, the Enron has a really high performance because the email has some easily learn patterns. It's like username at domain. So when the emails in the Enron data set shares the same domains, the recovery rate will achieve really high. And we also try the SSN in the AI for privacy datasets, but you know SSN contains 9 numbers, so it is really complex. So when the model memorize the SSN numbers, the precision only can achieve less than 5%. I think maybe it is due to the different complexity of the tasks.
Yeah, it makes sense. Okay, any other questions? I see one from Severin. Could Janus be? Oh, I lost it because I'm on my phone. But there was a message in the comment. I'd quickly bring it up. But did you see the question there? Okay, I got it now. So the question was, could Janus be enhanced to hackers' liking? So I guess like how extendable is the platform for for performing new attacks and stuff?
Sorry, I don't know what's the meaning of hackers' liking.
I mean, somebody trying to do an attack. I guess how extendable is the platform, and or how extendable is these concepts, and how could it be customized and further built upon for malicious intent?
You mean how can it be applied to the real world adversary?
Yeah, I guess that's one way of framing it. Yeah.
Yeah, maybe. Just for example, maybe now I can steal some private information from like a hospital and a bank, just 10 PIs. And then I can fine-tune these PIs to the model released by the hospital or the bank, and then I can recover other PIs because there is association between my fine-tuned data and the recovered data. So it can help the model recover other data, which I do not know. So I think maybe it's a realistic scenario when the model are actually trained on some sensitive data from some sensitive affiliations.
That makes sense. There was another question from Naman, but actually I think was already covered in the talk, which his question was, how does the vulnerability of the model depend on the model size? But you mentioned before that because larger models are able to memorize more information, that these larger models are typically more vulnerable to these PII attacks. Although conversely, the bigger, more successful models, when they're proprietary and when they're hidden behind an API, seemingly typically have bigger guardrails in place to prevent such attacks. So I guess there's two answers to that question. In a white box manner, so when the weights are open, in a white box manner, larger models are more susceptible just because they have more information stored. In practice, maybe the bigger models are less susceptible because more effort is put to make them more protected behind the API. So I can maybe just kind of come in with that a little bit. Good question on my side. So how do you think? What is the best defense to this, do you think? I imagine that obviously you want to make fine-tuning possible. So I imagine that probably what you want to do is enable fine-tuning, but you kind of maintain a small model that intercepts the requests. And that model stays the same. And that model is purely fine-tuned for safety reasons. And it like returns, sorry, I can't answer this. Sorry, I can't give private information. Sorry, I can't do this. And it kind of returns that. And if that model kind of says, no, this is fine, then it goes on to the fine-tuned model. And it never hits your custom fine-tuned model unless it's gone through this kind of smaller safety layer. That's one way that you could, for example, enable fine-tuning, but still prevent malicious usage to kind of uncover personal identifiable information. What are your thoughts on the best ways to circumvent this kind of attack, and how do you think GPT-4o are doing it?
As I think, as I just mentioned, that fine-tuning is necessary because we have some needs that we need the public released model to use on some local scenarios like a hospital. Maybe we can fine-tune. We need to fine-tune the public models on our local data, which always contain the sensitive PIIs. So in that time, we assume that the defender can have access to the white box of the models. So my solution is that I just try that I random labeling the data sets. Is that, for example, our Phantom data set is that tell me the email address of John Doe and it answers Zhang at like gmail.com. But we can random labeling the QA pairs. It's like tell me the email address of Zhang and it answers Jendo at gmail.com. Then we randomly labeling all the data set to do the machine learning on the phantoming phase. So we try it, and this performance is better than just do the answer like sorry I cannot understand it. I think sorry I cannot understand it. This answer is really easily broken by the easily phantoming. So maybe random labeling is a better solution. But the question is that it will improve the hallucination of the other return set. So we need to explore the trade-off between the privacy and the utility.
Yeah, no, makes a lot of sense. I hadn't really thought about that actually. Of course, when you're fine-tuning a model, you might want it to be able to answer with as you're saying, like you might need it to respond with personally identifiable information because it's a kind of locally on-prem deployment where you need to talk to your personal data, right?
Yep.
So you kind of need the fine-tuned model to be able to actually respond with personal information. You just want to make sure it cannot respond with personal information that was in the pre-training corpus that isn't related to your particular use case. And trying to get that balance is very difficult. And I guess having some arbitrary safety layer between yourself and the actual fine-tuned model is very restrictive, because then it probably is just going to not let you talk to your own private data. And this is where maybe like fully open source models might be more advantageous, because then you have the full white box access. But even then, if Meta have bought a load of private data from companies and like that data is then recoverable from the open source models, that's also not great. And it does make me wonder, obviously there's this open source data set that you described, which has like 70% recovery rate, which is known data, which is available in online publicly. But of course, OpenAI have bought lots of data from private sources. And I wonder if any of these companies are doing their own internal data set. You know, let's say these companies run your experiment on their own personal data. It'd be interesting to know what percentages they would get, and presumably it would be non-zero. So presumably there is the ability today to fine-tune a GPT 3.5 model and kind of uncover personal information from data that's not public, which is also very interesting, what that implications are. Yeah, very, very interesting. I guess final broad question, where do you think the research space of adversarial attacks for LLMs are going? What do you see some of the most interesting trends going forwards beyond just kind of fine tuning to prevent these guardrails from kicking in? Yeah.
I'm not sure. I just try some machine learning techniques to remove the private information. Maybe there are other techniques. So I would like to brainstorm with you to maybe find more interesting techniques to prevent the data leakage. Maybe I think the moderation system applied by OpenAI is really useful. Yeah, it's like we cannot attack.
How do you think this moderation system works? What's your best guess as to how they've implemented that?
I think it just detects some malicious text, maybe regarding containing the private information and misuse information.
And that's there with fine-tune as well?
Yeah, I think so.
Yeah,
because we just try the GPT for those APIs, and you know the GPT-4 APIs are only open for the authorized users. So it will monitor every submission of your uploaded data. So when you upload your data, I think it will carefully inspect this data to avoid the private and misuse concerns.
Yeah, makes sense. Yeah, really interesting. I certainly don't have any genius ideas, but it's yeah, I hadn't thought about it quite like this before, where it's very clear that yeah, you need to be able to fine tune to answer with very personal data, because in a way, like one of the main reasons to do fine tuning at all is because you need this very customized stuff on your own custom data, which is necessarily kind of private. So yeah, yeah, I don't know. I find it very interesting. I guess it's going to become increasingly important for the API providers and also the fine tuned. I actually think to some extent the Llama models. I don't know if Meta is buying proprietary data in the same way that OpenAI are, but obviously, like nobody really knows exactly what's going on in this kind of massive matrix of hidden weights. I mean, you know, more weights by starting to be orders of magnitude more weights than there are people on the earth in these models, and obviously no one really knows how data is represented there. So whether or not things can be probed, there is some kind of, you know, training corpus, and if that data is sold to Meta in a way that kind of maybe has some non-disclosure aspects to it or something because they don't want it to be public, then it starts to get into murky waters if these models can actually be retrospectively jailbroken. And also, like, similarly to like how, you know, the whole of authentication and like cracking authentication keys and everything could become, there's lots of data that could become hacked into once, you know, quantum computers make cryptography much faster and so on. There might be the same case with these LLMs, maybe like 405B from Llama. Actually, in 10 years' time, all of the data that was used to train that can be kind of extracted from the weights, and like it's actually not going to be private data at all. You know, I could easily imagine a world where that's the case. Yeah, it's very interesting. Anyway, I know we're getting close. I guess one final question. Yeah, Kato, you got a question?
Yes, hope you're hearing me.
Yeah.
Yes,
yeah, so
I wanted
yeah.
to ask, what is your view on AI safety? What is going to be the most crucial factor in maintaining AI safety for the coming decades?
Well, it's a so big question. I cannot answer it.
The predictions don't have to be right. I don't think people are going to be quoting you on this video in 10 years' time. So
it's okay. It's okay.
Yeah, well, we are focused on the privacy question about the AI safety, and as we to my best knowledge, I think the really eliminate the private privacy leakage is hard. It's really hard, because we tried many unlearning techniques and also model editing techniques to maybe to try to remove the neurons related to the sensitive information. But it can be easily recovered by some defense, by some attack techniques. And also, I think the Google DeepMind also proposes a new paper, a really new paper. It says that they can break the unlearning technique by a simple in-context learning technique. So I think the data cannot be really forgotten by the models. So it is really hard because it is a black box for us. The large language model is a black box for us. We don't know the data where the data is stored in. So we cannot deeply remove it in contrast. So that's my concern. So in the next step, we will keep focusing on how to prevent the privacy leakage in the large models. Yeah, that's all from my side.
Makes sense. Well, I think that's a perfect one to end on. So again, let's all give a very big round of applause to Xiaoyi. That was, yeah, really amazing talk. I have to say, it's definitely made me think about things quite differently. Yeah, some things I hadn't thought about there. So yeah, we'll definitely be eagerly continuing to follow on with your research, and we'd love to have you again presenting another paper, of course, at some point, Xiaoyi. Okay, well, yeah. Hope everyone has a good rest of today. Again, it was amazing having you with us, Xiaoyi. Thank you very much for joining, and we'll no doubt have another session at the same time next week. So yeah, have a good week, everybody. Have a good weekend, and bye for now. Thanks a lot. Bye-bye.
Thank you.